Okay, so here's a cool problem. So we've got a reaction, and we're not told the rate constant, but we're told that the rate constant doubles as the temperature goes from 17 to 22. And that's pretty typical, actually. The higher the temperature, the more molecules are smashing into each other with the activation energy. So as the temperature goes up, the speed of the particles increases, and there's more likelihood of a reaction. So how do we calculate the activation energy from this? And the activation energy, remember, that's the barrier to the reaction. And so the higher the barrier is, the slower the reaction is. The hotter the temperature, the more likely you can go over the barrier. So we can go ahead and we can plug into our equation that we just derived on the last slide. And so that is the log of K1 over K2 equals the activation energy, the thing we want to know, over the gas constant times by, well, you know what? We can use the form we just derived. T1 minus T2 over T1 times by T2. What are we given in the problem? Well, we are told at 17 degrees C, and our other temperature was 22 degrees C, we're told K doubles. Okay, and so we don't actually know K1 and K2, do we? Now, the thing is, if K doubles, then that tells us that we do actually know this ratio. And so K2 over K1 is 2. And if you look at the expression above, we want K1 over K2. And so we can write that, if we like, as 1 over 2, just the reciprocal of what we had there on the right-hand side. The temperature, we got to get those in absolute temperatures, don't we? And so 17 plus 273 and 22 plus 273, that gives us the Kelvin temperature. And let's see, so that's 290 Kelvin, and that is 295 Kelvin. Okay, so we're asked to solve the activation energy. Now, you know, depending on how comfortable you are with algebra, you might want to go ahead and just rearrange the expression for the activation energy and then just substitute in all the values at the end. And so why not do that, right? I mean, what's the point of suffering through algebra if we can't use it to make our life easy? So this is our expression, and we are trying to solve for the activation energy. So that means that we need to rearrange all of this so that EA is the subject to the equation. So what do we want to do? Well, we want EA by itself. Okay, on the other side, we've got the natural log of K1 over K2. And how are we going to get it all by itself? Well, R we need to bring up to the top of the other side. So if we multiply both sides by R, okay, that gives us the EA without the R term. And we want to get rid of these temperature terms. If we divide both sides by this, that puts it underneath there. Okay, so that's T1 minus T2 divided by T1 times by T2. So with a little bit of algebra, we can go ahead and we can get EA all by itself. All right, at this point here, we can plug and chug everything in there. The natural log of those rate constants we saw was the natural log of a half. R is 8.314. And, you know, I like to put the 5 on the end. I think, why not have an extra significant figure? Those units, those are joules per mole Kelvin. Okay, I got my temperatures on the bottom. T1 was my original temperature, and that was 290 Kelvin. T2 was my final temperature, 295 Kelvin. And we're dividing that by T1 times by T2. Okay, so we got a mess to calculate here. Let's just look at the units before we jump too far into it. The units on the top, those are joules per mole Kelvin. And if we look at the bottom, it's kind of a mess. We've got Kelvin minus Kelvin. And so when we subtract Kelvin from Kelvin, we have units of Kelvin. And on the bottom, we've got Kelvin times by Kelvin. And so that's Kelvin squared. Okay, so we can go ahead and we can work a little bit harder on that. So that's joules per mole Kelvin on the top. And on the bottom, we've got Kelvin over Kelvin squared. We know that one of these Kelvins cancels, so that gives us 1 over Kelvin. And at this point here, I guess we've got some nifty fraction work here. So we've got joules per mole Kelvin. And you know what? If we're dividing by a fraction, that's like multiplying by the fraction upside down. And so we can go ahead, if we're dividing by 1 over k, that's like multiplying by k over 1. And oh goody, the Kelvin cancel, and we are just left with joules per mole. And so with that, we know our activation energy is going to have units of joules per mole. And if we plug into the expression above, and we go ahead and we throw all the numbers in, and we end up keeping track of significant figures, we should get 98,600 joules per mole. It is traditional to write, rather than joules per mole for activation energies, kilojoules per mole. And if you remember, kilo means 10 to the 3. A kilojoule is 10 to the 3 joules, or if you like, 1,000 joules. And so we can convert this to more typical units by basically dividing by 1,000, so that's 98.6 kilojoules per mole. So after all of this, we've calculated the activation energy, the barrier to the reaction. Now, it turns out 100 kilojoules per mole, that's a pretty serious activation energy, actually. Probably most reactions will be a little bit lower than that, but at least ballpark, I would expect activation energies to be in the 10 to sort of the 100 kilojoule per mole range. Okay, that's it about the Arrhenius equation.